Hello everyone. In this lecture I shall discuss the extended Euler's method for solution of pair of equations and the solution of second and higher order differential equations. If we recall the Euler's method, basically we used Euler method to solve the first order differential equations with initial conditions. Okay, the necessary formula for this usual Euler's method is yn plus 1 is yn plus hf xn yn and n greater than equal to 0. Now we extend it for pair of equations as well as for the solution of second and higher order differential equations with given initial conditions. Okay, before the details of discussion, let me to introduce myself, Professor Susanta Kumar Paikray, currently working as a Professor of Mathematics at Veer Surendra University of Technology, Burla, Odisha, India. So without much delay, let us discuss the extended Euler's method for solving the pair of equations. Consider the system of equations. Consider the system of two first order differential equations with initial conditions. Here dy by dx is equal to f of xyz and here dz by dx is equal to g of xyz. You see, we have a z here and we have a z here. Okay, we have a z here. You see it. So now with the initial conditions, with initial conditions, y of x0 is equal to y0 and z of x0 and here z of x0 is equal to z0. Okay, and we need to solve it. Now the approximate values y xn plus 1 is equal to yn plus 1 and z xn plus 1 is equal to zn plus 1 can be computed stepwise as follows. So in line with the Euler's formula, this is the Euler's formula. We have the formula for the extended method. Here yn plus 1 is equal to yn plus hf xn yn zn. Right, this zn here in zn plus 1 is zn plus hg xn yn zn. So for computation of this zn, we have to depend upon this. Okay, in the subsequent stage. So the formula for your extended solution by Euler's method for solving pair of equation is like this, and your n greater than is equal to your 0, right? So now we extend this technique to the second order differential equations. Okay, to the second order differential equations. So we consider the second order differential equation. We consider d square y by dx square is gxy y dash with conditions y of x0 is equal to y0 and y dash of x0 is equal to y dash 0. Now what we do, we put this is equal to z. Okay, we put this is equal to z and convert it into the pair of equations. Okay, put y dash is equal to z So this implies here this d square y by dx square, it will become here z dash, it will become here z dash is equal to g x y, it becomes here z, right? So what we are getting, that means here dy by dx is equal to z and dz by dx is equal to gxyz. So it converted to pair of equations. It converted to pair of equations. Once you convert it to a pair of equations, what you will do? So to solve this, okay, we just use the previous formula. Okay, we just use this previous formula and continue the solutions, right? So if we solve some solved examples, then your idea will clear. So let us solve some examples. Now we need to use the Euler's method. We also call it Euler's method or extended Euler methods to solve this. This is a second order differential equations with initial condition yn is y1 is 0.77 and your y dash 1 is minus 0.44, and we are asked to compute y of 1.1, 1.2, 1.3 and 1.4. okay, so coming to the solution, consider y double dash plus y dash by x plus y is equal to 0. As we know, we put y of 1 is equal to 0.77 and y dash 1 is equal to minus 0.44. So now you put y dash is equal to z. Okay, so this implies this will be your z dash plus this will be your y by z plus your y is equal to your 0, right? So that means your z dash is equal to your minus of y by z minus of y. Sorry. So this is actually your z by x. It is your z by x plus y equal to 0. So what is your z dash? Bringing this to right hand side, it is minus z by x minus y, and it is my gxyz. It is my gxyz, right? It is my gxyz, and this is my fxyz, isn't it? This is my fxyz. So here you see the interval is initial point is 1. It is 1. We have to extend up to 1.4. So we'll extend from 1 to 1.4. okay, so we take the step length h is suppose 0.1. Let my h is equal to 0.1. okay, we have the Euler's formula. I mean to say here is the extended formula. Here yn plus 1 is equal to yn plus hf xn yn zn, and here zn plus 1 is equal to zn plus hf hg xn yn zn. okay, so this is the formula. So now in view of this, we have our this is our f, and this is our g. In view of this, we modify the formula. So this implies my yn plus 1 is y1 plus h xn yn zn is simply here zn h zn, and here zn plus 1 will be zn plus 1 will be here zn plus h. Now g of xn yn zn, it will be what? Minus of zn by xn minus yn. okay, minus yn. And with here n greater than is equal to 0, right? Now coming to, now this formula is reduces to this now, okay? This formula is my reduces to this. So what is my y1 now? What is my y1 now? Means y of x1, what is x1? x0 is 1, x0 is 1, so it is 1 plus h means 1.1, y of 1.1, so this will be equal to here y0 plus h z0, right? What is your z? So now what is my z0? Now this will converted to your z0, is not it? So what is my z0 here? So z of, because y dash is z, so z1, z of 1 is equal to minus 0.44, minus 0.44. So this is my z0, right? This is my z0 and this is my x0. And for this, what is the condition? This is the usual condition. Here y of 0 is equal to here 0.77. So this is your y0 here. This is your y0 here, right? So now we use it. So this will be y0 is here 0.77 plus h is here 0.1 into z0 is here minus 0.44, minus 0.44. If you simplify it, it will 0.726. Okay. Now we compute z1. So what is my z1? So from this I compute this. From this I compute z1. So z1 means your z of x1 means your z of 1.1. And it will be given by the formula. You see, it is z0 plus h minus z0 by x0 minus y0. It is here y of 1 is equal to this, means this x0 is here 1. Okay, x0 is here 1. So here the z0 is here minus 0.44. So it is minus 0.44 plus h is here 0.1 into, so it is plus 0.44 minus of z0 by x0 is here 1 minus y0. y0 is here 0.77. If you simplify it, this will be here minus 0.473. Okay. So at this next step, so it is my step 1, I say. It is my step 1. So it is my step 1. In step 1. In step 2, here my n is equal to 1. For n is equal to 1, here n is equal to 0. So with n is equal to 1, in step 2, what is my y2? y2 is y of 1.2. It will be x1 plus h z1. And here z2 will be from this. Here z2 will be z of 1.2. So this will be z1 plus h into this formula minus of z1 by x1 minus of y1. So here z1 will come from this. Okay. So that's why the simultaneous equation is needed here. Simultaneous. So z1 will come from this. If we simplify it, here x1 is 1.1 plus h is 0.1 into z1 we calculate here it minus 0.473. If you simplify, we will get, it is here y1 plus. It is here y1 plus. Okay. So it is y1 plus. So this y1 here is 0.726. So now if we simplify it, it will be 0.726 minus 0.047. So this is equal to here 0.679. Okay, 679. So now coming to my Z2, it will be here Z1. Z1 is here minus of 0.473 plus H is here 0.1 into here minus of Z1 means 0.473 divided by here X1 is 1.1 minus Y1 is 0.726. If I simplify it, it will be minus 0.473 minus 0.1 into 0.296. So this will be equal to minus 0.503. Okay. Now in step 3 for your n is equal to 2, what I am getting here, y3 is equal to y of 1.3. So this will be y2 plus hz2. So this z2 will be substituted here. Okay. So now here accordingly here z3 will be here z of 1.3 and it will be z2 plus h minus z2 by x2 minus y2, and y2 is here, and if I simplify it, I will get, it will be my 0.629. if I simplify it, it will be my minus 0.529. Now coming to the last step, here step 4. So coming to the last step, here for n is equal to 3, here y4 z4 is y of 1.4 and z of 1.4. So it is the last one. We need y of 1.4. So we have the formula in the similar way. We are getting it is 0.576 and it will be minus 0.551. Okay. So this is our answer here. So similarly you can solve the similar problems. So to conclude, like the Taylor series method, we have the solution of second order, and for this pair of equations with less effort, once we know the Euler's method, with less effort we just extend it to the higher order differential equations. Okay. So at this stage we should conclude our lecture. So if you feel this lecture is helpful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lecture for your benefit. So thank you all. Have a nice day.